Alright guys, what's up? So today we're going to do something a little interesting. We're going to actually go over a motion of a spring. So usually the way they model springs in science is like this. Where you have like a little box, I guess, and you have like a little spring. Now, usually the way they model a spring is based on like the sine and cosine functions to find like an equilibrium position. So, without going to like the whole derivation or the history behind this, essentially everything usually gets modeled down to this formula. So you have an x is equal to a v naught, they call it, over omega, and I'll explain what all this is. Then omega t, and then plus x naught cosine omega t. Now v naught is just a velocity, and then this omegas, these are usually just like the stiffness or the amount of the weight, basically. Actually not really. It's just it's kind of hard. I guess you could say it depends on the stiffness and the weight, you could say. So this is relying on, I guess, the x or whatever. It's kind of weird. And then this t is just time. So basically, this is a starting position. X naught is the starting position, and V naught is just sorry, it's the starting velocity. And omega just depends on the weight and the stiffness. So let's do a problem really quick on it. So let's say you're given a velocity of 3 centimeters per second from a position x naught of 2 centimeters. Now, you assume, so usually for omega, they'll usually give you like a value for it. So in this case, it says assume that the spring and weight combination, the constant omega, has a value of 1. So you essentially assume omega is just 1. So now they want you to find, you got the formula, which is you already did here, and then they want you to find the location of the weight, which is this, 2 seconds. Sorry, no, 2 seconds after the weight is set in motion. So you're essentially already given everything, kind of. So you have your x naught, your v naught. Oh, I forgot to put naught here, but that's what it is. Omega is given, and then t is given. So now all you do is plug them in. So you have 3. Well, since it's over 1, you don't really need to do over 1. That's that. Then you have sine. Then you have times 2 after 2 seconds. Plus 2 cosine 2. And once you do the calculations and you're calculating your TID4, your calculator, you end up with a negative 3.6 centimeters. The reason is because once you do when you do the sine and cosine, you get like, I think it's with the sine, you get like a negative number. So that's why, this comes out kind of weird. So you end up with, so essentially, don't be scared of the negative. All this is saying is that this thing is 3.6 centimeters below equilibrium. So it calculates an upward in equilibrium as positive, and then downward in equilibrium as a negative. So don't be scared of this. It's just saying that, oh, it's going down 3.6 from the equilibrium. So that's it. And this is actually a little bit of a, well, I learned it in upper division. I mean, you learn this in like basic physics, but this is what we learned when we had a class on springs, and this was basically like the ultimate formula. So basically, this is like the basic formula foundation, and then from there you just work through different variations. So this is actually a pretty important formula in science. So yeah, I mean, hope you guys enjoy that, and we'll see you guys in the next video.